Hello again. So, let us continue our discussion of this detour of finite variable optimization, necessary and sufficient conditions without constraint, unconstrained minimization. We discussed necessary sufficient conditions. Now, let us take this one variable problem and do a numerical example that is shown here. F equal to half kx square minus PL times 1 minus cosine x. This is our f of x here. We have taken an example. Okay. Now, if I do f prime, which is in our notation df by dx. Okay. So, what do we get here? Half kx square, half and this 2 in x square will cancel. So, I will have kx. Okay. And then we have PL, which are constants, x is the variable here. So, we have minus and there is minus. When I take derivative of cosine x, I get another minus. So, minus minus minus, eventually I have minus P L sine x. That should be equal to 0. That is our condition for x to be a minimum, right, necessary condition. If you solve this thing, so kx minus PL sine x equal to 0. If you just observe this equation, x equal to 0 is definitely a solution, right, because kx equal to 0, PL sin x is 0 when x equal to 0, that is a solution. Is it the only solution? Clearly not, because if I imagine that for some values of P and L, let us say I draw a sine curve. So, we got the necessary condition that kx minus PL sin x equal to 0, x equal to 0 is a solution, let us call that x star. Okay. Is that the only solution? But if you look at kx and PL sin x, let us draw for some value of P and L, we can draw the sine curve, and in fact it will go both sides, right. And then now if I take a value of k that is very large, I will have a straight line like this. Now, these two are intersecting only at the origin x equal to 0, but if k were to be different, let us say, then I have one more and third, right, where these two things are equal, that is what we are saying, right. Kx should be equal to PL times sin x. There can be multiple solutions. So, for a simple one variable problem, there can be multiple solutions, some of them will be minima, other will be maxima or in between. For that, we have to take the second derivative, that is d square f by dx square. Okay. That in this problem, if I take derivative of this one more time, I get this k and then minus PL cosine x. Okay. So, here at x star equal to 0, cosine x star will be cosine 0 is 1 and then PL. So, if I have k minus PL should be greater than 0 for this point to be a minimum of this function. Okay. So, as I increase P, at some point k is let us say chosen such that that is larger than P times L for some value of P. As you increase P, at some point this will cease to be positive, in which case this point, which is a minimum until then, will cease to be a minimum, and then when it becomes negative, it is going to become a maximum according to our sufficient condition, right. We use necessary condition to solve for the problem, to get all these values of x star. Okay. Here I did graphically, but you can do it analytically or numerically, and then every one of those you have to check against the sufficient condition we have written and then verify whether it is greater than 0, then it implies that it is a minimum. Otherwise, if it is less than 0, it would imply it is a maximum. Okay. So, you should work out this numerical example yourself to see as you vary the value of P, how x star, which is 0, goes from a minimum to maximum. It is in fact, it is a wonderful simple example that illustrates buckling of, if I have a rod which is hinged over here, and let us say there is a torsional spring here of constant k or kappa. Then if this length is L, this is a rigid rod here, there is a compressive force P. For that, this is the potential energy, as we considered minimum potential energy principle gives you static equilibrium. We are actually minimizing this F, which is actually the potential energy for this problem. Okay. So, you should work it out and understand how minimum maximum change as you increase P. As you increase P beyond a certain threshold value, which is equal to k by L, then it is actually a buckling. Then what is straight will suddenly shift that side or this side. Okay. You should really try this problem out. It is a one variable optimization problem. Okay. Now, let us move on to two variables x and y. Okay. Since two variables, let me change the color of the ink. Okay. We have two variable problem. For that, let us do the Taylor series expansion. Okay. And that is how it looks, right. So, we have the zeroth order term which is in blue color, and then the first order term, there are two of them, there is 1 and there is 2. When I write f x here, this f x, what I mean is that it is dou f by dou x. Okay. F sub x, this is our notation. Similarly, if I write f y, I mean this to be dou f by dou y, partial derivative. So, here I can do the perturbation in delta x star, delta y star, right. We remember that we had a disk in two variables. I can from this point that I have. So, we had a disk around a point. If I move somewhere, I will have a delta x star, there is delta y star, which is what is indicated here. So, this is delta x star, this distance, and this distance will be delta y star. Okay. That is a zeroth order term, and a partial derivative with respect to x, partial with respect to y. Now, in the case of second order term, we have three terms, there is 1, there is 2, there are 3, right. So, this is delta x star square, perturbation in the x, then y, this is x, this is y, second order term, and this is mixture delta x star and delta y star. Okay. So, we have three terms in the second order term. Now, again if you say the first order necessary condition that these two terms should be equal to 0, because if delta x star, delta y star are very small, we can neglect the second order term and higher order terms. Then the first order term, because you do not know delta x star, delta y star can be positive or negative depending on the sign of dou f by dou x and dou f by dou y, we do not know whether the function will be larger or smaller. So, we require the first order condition. So, we say that both f of x and f of y should both be equal to 0, that is the necessary condition here. Okay. All the notation f x, f y, f x x is second derivative with respect to x, f x y mixed derivative, second derivative dou square f by dou x dou y, and then dou y y is dou square f by dou y square, okay, which is how we have written. Now, we can write in the matrix form like this. So, we have arranged this in the form of a row vector and this as a column vector. So, that when you multiply I get these two terms, right. So, these terms I get, and likewise if I write this second order term which has three terms in it in the form of a matrix with a row vector and a column vector, and this is a matrix here, a 2 by 2 matrix in the case of two variables, right. So, let us look at that. So, we have written this in this shorthand notation. Again this is zeroth order term and this is first order term and this is second order term, and these are third and higher order, right. When we have this, we write it in the form of this row vector here, right. So, which I have written as transpose. So, what we have written here, this thing is called the gradient. Okay. Likewise, we have indicated this matrix here with the letter H, which is called Hessian. Okay. We have a gradient and a Hessian. Gradient determines the first order term, Hessian determines second order term. Now, when if we want first order term to vanish for x star y star to be a local minimizing point, then the gradient should be 0. Just like in the one variable case, we said df by dx should be equal to 0. Here we say gradient, so that becomes necessary condition. After necessary condition goes away, we want our f of x y here, that should be larger than f of x star y star. Now that this has gone to 0 because of necessary condition, then the second order condition term that we have, that is this whole thing here, that has to be greater than 0, because only then x star y star will be minimizing point or minimum value, right. Every other value should be larger, that is a sufficient condition as we had seen, and that is the meaning. So, after the first order term goes away, second order term should be positive, that makes x star y star a minimizer. But understand the gradient, which is the partial derivative of f with respect to x and y, and the Hessian, which is second order partial derivatives, which we will see what we have written, gradient and Hessian, which I have overwritten. Let me erase it so that you can actually see. Yeah. So, now, so you have that as a gradient and this is the Hessian. Okay. We get the pen back. Yeah. So, this is gradient, which is a vector, you see it is a array in this case of size 2 by 1, okay. And the Hessian is a matrix, in this case it is 2 by 2, right. It is a gradient, which is actually the direction in which this function at that point changes the most, that is a direction. It is a 2 by 1 array column vector, or it is a vector if we say x and y are two directions, that is a gradient. It is the direction in which the function changes its value at the fastest rate. Okay. Hessian is second order term, has this thing called Hessian, which is a 2 by 2 matrix that includes all these second derivatives x square, y square, and then x y. Necessary condition is that the gradient should be equal to 0 for the argument that we have described now, right. So, this is a vector. So, it should be equal to a 0 vector, meaning that there are actually two scalar equations in it, means that f x is 0 and then f sub y is equal to 0. Again, do not forget the notation, f sub x is dou f by dou x and f sub y is dou f by dou y. So, that is a necessary condition. Okay. That is what we have written here, right. These are the necessary condition in two variables. When you are solving two variable optimization problem, you have two unknowns, you do not know x star, you do not know y star. So, you need two equations, which is what we have. We have two equations to solve for two variables, to solve for x star and y star. Okay. Two unknowns, two equations, that is what these conditions are useful for. Not only you can tell whether a given point is minimum or not, but also you can use these conditions, necessary conditions, to solve for those minimizing point. Now, when you go to sufficient condition, then the second order term, which is what we have shown here, right. When we expand it out, it will have three terms that we get. Now, this one, for any value of these perturbations delta x star and delta y star, which are over here and here as a row vector and a column vector, when you expand it all out, then you get the three terms. The sum of that, which is a second order term, should be greater than 0. That is sufficient condition. So, which in shorthand notation looks like this. For any is important, any small perturbations, these are small perturbations, for any small perturbations this should be true, and all this if it is for any values of these, right, then if it has to be greater than 0, the property lies within this matrix Hessian. Okay. That property is called positive definiteness. Okay. Definitely positive, that is, no matter what values you take for this f of delta x star delta y star, okay, this whole quantity that we are taking a row vector and then a matrix and a column vector, that will be greater than 0. If it is true, then we say such a matrix is positive definite at that point, right. We are doing x star y star, evaluate at that point will be called positive definite. So, if I have, let us say, problem where function f is a function of two variables x and y, then if locally if it looks like a bowl like this, okay, let us say this is my x star y star coordinates. At this point, or whatever surface that f of x y can be represented as a surface in 2D x and y, and then third dimension f of x y, locally it will look like a bowl which is the bottom of a valley, that is a minimum. Condition for that is this should be greater than 0, that means that h is positive definite, that corresponds to a minimum, and that is the sufficient condition for two variables. What was second derivative is simply greater than 0 over sufficient condition, that is d square f by dx square greater than 0. Here this matrix should be positive definite, meaning that this thing should hold, okay, that is positive definite. But what if it is not greater strictly, but greater than or equal to 0? Such a thing will look like this. Okay. So, it looks like a fold, right, like a valley fold as we call it. Then we call the matrix H positive semi definite, it is greater than or equal to 0. Okay. Then you can consider other possibilities. Now, consider strictly greater, in this case a minimum, greater than or equal to, it is a valley fold. Okay. It is either minimum or a flat, that is, if I look, if I come in this way, right, whatever point I take, it looks like a minimum, but if I come like this, it is flat, it does not change, because its second order term is 0 in that direction if I perturb, right, that is the valley fold. Similarly, if it is strictly less, then it corresponds to a maximum, right, then you are at the top of a hill, peak of a hill, you are the king now, you are the top, right. In that case, actually you are a king, but it is negative, it has negative connotation, negative definite. When a matrix satisfies this property where it is strictly less than 0, for a negative definite, that corresponds to a maximum at the peak of a hill. Now, we can talk about negative semi definite, right. Then it is not strictly less than 0, that is second order term, it is less than or equal to 0, that is a ridge or a hill fold. So, any point here going this way, it looks like it is flat, okay. But if I go in the other direction, that is if I go like this, then actually you have maximum or a flat, okay. Now, there is another one, right, where this is just equal to 0. So, no matter what delta x star and delta y star you take, this matrix H at that point has a property that it just gives you 0. In such a case, locally the surface looks like this, plane, okay, plain old plane. So, that is there just flat, then it is neither a minimum nor a maximum, neither a minimum nor a maximum, right. So, such a thing can also happen. There is one more case you can think of, which is, before that let us first consider the 5 cases that we have considered. Positive definite corresponds to a minimum, positive semi definite corresponds to a minimum or a flat region, negative definite corresponds to a maximum, negative semi definite corresponds to a maximum or flat, null definite, okay, there it is just flat, neither minimum nor maximum. Look at the condition, greater than 0, greater than or equal to 0, less than 0, less than or equal to 0, then equal to 0. Okay. So, all that is contained in this Hessian sufficient condition. Now, there is one more, right. So, we have all of these again, a bowl, a valley fold, a maximum like a hill, hill fold and flat, that is what we had seen pictorially. There is one more something like this, right, which we call a saddle point. If we are here going this way, you see that it is a maximum, but coming this way it is a minimum. So, the point is the Hessian now is indefinite, it is not able to decide. That is, if you take arbitrary values of delta x star and delta y star and do this multiplication, which leads to a scalar, because this is a 2 by 2 matrix, this is a 2 by 1 vector, this is 1 by 2 row vector. So, overall you will get 1 by 1, right, a scalar that we do not know whether it is greater than 0, less than 0 or equal to 0. So, that is kind of an indefinite matrix Hessian, in which case we call it a saddle point, or this point is called a saddle point. That is how the horse's saddle looks like. Okay. There our f is neither a minimum nor maximum, or rather it is both a minimum and a maximum, right. Coming one way it is minimum, other way it is maximum, right. It is not absolutely minimum, absolutely maximum, it is both. Such a thing is called a saddle point problem, saddle point example. Okay. So, for you, if you have not seen a saddle, that is how it looks like here, right. So, it is a minimum that way, going that way it is a maximum. Okay. That is how a horse saddle looks like, but you do not have to go and look at a horse saddle if the horses are not close to you, but you can always see the chips, right, the Pringle chips, but most of the chips have this profile. Most likely they pack them so that they do not break before we bite and break them. So, they do this. These are all the saddle things that you can clearly see. Okay. Minimum this way, maximum that way. Okay. Now, let us do a simple example in this 2 variable case. Now, instead of putting as x1 x2, I am writing as x1 x2, writing xy that we had taken, does not matter, 2 symbols xy or x1 x2. If I want to minimize this function with respect to x1 and x2, okay, first thing is necessary condition that says that we have the gradient, right. So, not a one variable problem. So, let me erase it. Okay. First I have to write the gradient of f, that means that I have to have dou f by dou x1, dou f by dou x2. What is it now for this problem? We distribute a partial derivative. So, that is 2 x1 minus 3 x2, we are taking derivative with respect to x1 plus 1, and then with respect to x2 we will take derivative of f, dou f by dou x2, that will be 3 x1 plus 8 x2 minus 1, right. Now, this should be equal to 0 0, that is our necessary condition. So, we get 2 equations that we can solve. So, I have to solve these 2 equations, 2 x1 minus 3 x2 plus 1 equal to 0, minus 3 x1 plus 8 x2 minus 1 equal to 0. If I solve these two, these are linear equations, I will get the answer x1 and x2. So, x1 turns out to be minus 5 by 7, x2 turns out to be minus 1 by 7, you can plug it in and then see. Now, if I want to know if this x star now, right. So, what is our x star? Our x star is minus 5 by 7 minus 1 by 7. If I want to know if it is a minimum or a maximum, because this necessary condition is what we have used. This is NC, right, necessary condition. We have to write sufficient condition to be sure. So, for that we need to write this Hessian matrix. That means that I have to do dou square f by dou x square, dou square f by dou x dou y, and then dou square f by dou y dou x, dou y is the same mixed derivative, and then dou square f by dou y square. If I do that, okay. So, I need to take dou f by dou x1, one more derivative with respect to x1, that will give me 2 here. With respect to x2, give me minus 3 here, again dou square f by dou y dou x, looking at this thing, right. So, it will give minus 3 and then 8. Okay. Now, according to our thing, we have to check whether this H is positive definite. We know the definition, but operationally useful thing, there are several. One of the easiest is to check the eigenvalues of this matrix H. If both of them are positive, you say it is positive definite. Okay. You can look at the principal minors and check the signs of it. If they are all positive, it will be positive definite matrix and so forth, but most easiest is to check the eigenvalues. In this case, if H, if you look at determinant, if it is positive and you look at the eigenvalues, both of them are positive, then I think we can conclude it is a minimum, in which case in fact this point x star turns out a minimum. You can plug it in and check, okay, that both eigenvalues of this H are going to be positive, and hence this point x star that we found is actually a minimizer for this problem. Okay. Now, let us jump to n variables, right. Then I can write the Taylor's expansion. We just have the summation now. If you see, this is the first order term, again our 0th order term and our first order term, and then I have our second order term and then higher order terms, right. It is the same thing now. The gradient will have a size n by 1 and the Hessian will have a size n by n, okay, and we have perturbations also are n by 1, right. So, this is n by 1, this is 1 by n, okay. This is n by 1 and we have transpose here. So, it is 1 by n, this is n by 1. So, we get a scalar eventually f of x. So, again if you think about our argument for necessary condition, we want this gradient to be equal to the 0 vector and we want this to be PD, meaning positive definite, for it to be a minimum, positive definite, except that we cannot imagine this bowl and a hill and a valley fold and a ridge fold and so forth. We just have to imagine that in the n dimensions, okay. Our n dimensions problem, they will be bowls and hills and so forth, valleys and hills and so forth, right. So, necessary condition for n variable problem is that this gradient in n variable should be equal to n by 1, right, that vector, this n by 1, this n by 1. So, we have n equations here in n variables meaning that we do not know x1 star, x2 star and so forth up to xn star. These are all the unknowns that we have, but we have enough equations, n equations to solve for all of them. And then you look at the Hessian matrix, which is now an n by n matrix, a big one. You look at the eigenvalues, if they are all positive, then you conclude that that x star that you found is actually a minimizer for the problem, that is f of x that you have, okay. It should be positive definite. One way to check is that all eigenvalues are positive for it. So, all eigenvalues are positive, or all principal minors are positive, all pivots if you reduce to row echelon form that you learnt in linear algebra, that is also there, but as I said, looking at eigenvalues is the best way, is the easiest way, because in many ways numerical analysis you can easily find them using software, not yourself, but you can find them. Again, to summarize, if it is a local minimum, then you will have quadratic form is positive and the matrix is positive definite, and the negative definite for a local maximum, positive semi definite for a valley fold, then eigenvalues are some are 0, others are positive. Here all of them are positive, here all of them are negative, here some of them 0 or positive, here some are 0 negative, then we have negative semi definite, okay. Then you get a ridgefold, and a saddle point there will be mixed signs for this. Okay. So, if you take a numerical example in 3D now, ND will be a little too much to solve in a few minutes. So, I took a problem where there are x1, x2, x3. So, let us write the gradient for this. So, this will be partial derivative of f with respect to x1, that will give you 2x1 and then 3x2 and then 4x3, okay. That is dou f by dou x1. Let us do dou f by dou x2, that is 4x2 plus 3x1 minus 3x3, derivative of f with respect to x2. Now, derivative f with respect to x3 will get 6x3 plus 4x1 minus 3x2, right. So, we have all of these should be equal to 0, 0, 0, each of them should be equal to 0, you get 3 equations and 3 unknowns, right. Here there is a trivial solution actually, if x1 equal to 0, x2 equal to 0, x3 equal to 0 actually satisfies this. So, we can actually call this, okay. It is one solution, it is a linear system, we have one solution. Now, whether this solution is a necessary condition, right, we need to look at the sufficient condition also. So, let us write the Hessian here, okay, that will be a 3 by 3. So, I have to write dou square f by dou x1 square. I already have with respect to x1 one derivative, that I will have 2 here and then 3 here and 4. With respect to x2, this will be 4, this will be 3, this will be minus 3 and this will be 6, that is dou square f by dou x3 square, and then this will be 4, this will be minus 3. This is our Hessian, okay. The eigenvalues for this which I have. So, we have the Hessian which is 2 3 4, 3 4 minus 3, 4 minus 3 6. Now, we have to look at the eigenvalues. So, eigenvalues of this matrix which I have computed ahead of time are these here. So, one is minus 2.95, 6.16 and 8.79. These are the 3 eigenvalues for this matrix. They have, this is negative, these two are positive and positive, mixed signs. So, this matrix is indefinite. So, in this 3 variable problem, we have this point which is like a saddle point in 3 dimensions. It is not your horse saddle, but you imagine a higher dimension. So, such a problem is not a minimizer, not a maximizer. In one direction, if I say x1 direction, it looks like a maximum because eigenvalue is negative, other 2 directions is positive. So, it is a minimum. So, it is a saddle point. Okay. Just to summarize, today we talked about unconstrained finite variable minimization or optimization, and we first talked about definitions and then we went to conditions. Definitions are not operationally useful, but they tell you the condition of a local minimum and a global minimum, and operationally useful definition or a condition we got it for the necessary condition and sufficient condition established from it for a local minimum, and then we talked about the concepts of gradient and Hessian. And in 2 variables we have graphical interpretation of peaks, valleys, hill folds and ridges and flat plains and saddle points. And mainly what we remember, you should remember, is that rules for checking partial definiteness which is based on eigen values, okay, which is the easiest. In the next lecture we consider the constraints also in n variables, and then after the detour we move on to calculus variations again. Thank you.